Hello. In the Tech Forum today, Soby Mathew and Alexei Fedorov will talk about the EL3 GPT Fusing discussion on various issues and approaches. Yeah, on over to you, Soby.
Thanks, Leah. Hello, everyone. I'm Soby Mathew. I'm the tech lead for the TF RMM project. And I also look at some RMA-related things in EL3 firmware. Along with me, Alexei from my team, he's also present for the presentation. He's done most of the implementation, so he will be able to help me with some of the implementation specifics of this particular talk. So with regards to agenda, first, I hope to give a small introduction on the granular protection table as described by the RMA architecture. Then I'll describe the performance issue. I'll also mention some proof of concept solutions that we've done in EL3 firmware, inefficiency of the 4 kilobyte delegation that we have today for the realm world, and also proposed upstream approach. I also hope to touch upon the fine-grained locks that we are implementing as part of the patch stack together alongside this work. Okay, so just just a brief introduction to granular protection tables. So the FEAT RMA introduces 2 new address spaces, which brings to a total of 4, namely non-secure, realm, secure, and root. Any CPU access, any access that the CPU makes, it targets the physical address in one of the 4 physical address spaces. And granular protection check, or GPC, is a mechanism by which accesses to those physical address spaces are checked. To do this checking, there is an in-memory data structure that describes the association of a physical address with the page, with the PA space, and that is known as the granular protection table. So as per the architecture, there are 2 levels of lookup. There is a L0 table and the L1 GPT. The architecture allows the L1 GPT to be either contiguous or granule descriptor. I've highlighted contiguous because this is important for the next slide. The L0 table is usually located in SRAM, whereas the L1 table, it can be located in DDR in a root pass carve-out. The current TFA implementation, it implements granule descriptor in the L1 table. This means that every page has a GPI in the L1 table. So the right-hand side picture shows the current scheme implemented by TFA. The BL2 bootloader, as part of initializing memory, it would create the L0, GPT L0 and GPT L1 tables. And the permissions would be set such that we have the boot carve-outs for each of the different security states. So there is the secure pass where the secure firmware runs from, the realm pass, which is usually which is for the RMM, and the root pass is for use by EL3 firmware. So BL2 creates these boot carve-outs as part of its booting process. And then at runtime, BL3.1 retains the carve-outs, whatever BL2 has created, and then depending on the requests received at runtime, BL3.1 will manipulate the L1 table to change the permissions so that addresses are now restricted to particular paths, either realm or secure, depending on the runtime requests. So that is a brief introduction to the GPC and the granular protection table that is present today. If there are no questions, I can progress to the next slide. Okay. So I mentioned, I highlighted the contiguous field previously in my previous slide. Now there is a performance issue if we use 4K GPIs in L1. Certain workloads will expect 100% hit rate from the SMMU TBU. And this is usually achieved by increasing the S1, the stage 1 and stage 2 page size so that the application footprint will fit entirely within the TBU. So the stage 1 and stage 2 page size can either be 2 MB or 1 GB depending on the mapping at stage 1 or a stage 2. Now, since EL3 does not create these GPT entries in these particular block sizes, it maps them as granules. It results in TBU misses under some workload footprints, and there is a performance degradation observed. So to give the application consistent hardware performance, it is necessary that the GPT entry at EL3 should more or less have the same size as the stage 2 mapping. Now, the trouble is this issue affects existing non-secure workloads, which are utilizing SMMU. It's not only the realm world use cases which are affected, but the existing non-secure workloads as well. And the working assumption is that TFA or EL3 firmware will be able to fuse the contiguous blocks opportunistically to avoid this problem. I have shown the format of the contiguous descriptor. So the L1 contiguous descriptor is as shown in the figure over there. And it can be either of the 3 sizes mentioned. So it can be a 2 MB contiguous descriptor or a 32 MB contiguous or a 512 MB contiguous descriptor. So today TFA doesn't do it. TFA maps all of the memory as in the 4K descriptor format at L1, and hence we have the performance issue. Are there any questions on this slide?
Related, but not direct question, right? Does TFA support using of these GPTs in SMMU? I haven't seen the code. Do we initialize SMMUs using the same GPTs as well?
So SMMUs are the stage 1 and stage 2s are mainly programmed from the hypervisor or lower ELs. There is a bit of initialization at EL3. Olivier, I think you know the details. Essentially, we program the GPT table base address to the SMMU, which has capability for RME extension.
Yeah,
so,
that's what I was asking. So we do program the base for the GPT.
Yes,
okay.
yes, yeah, this is done. Yeah, yeah. Okay. There are no further questions. Can move on to the next slide. So essentially, EL3 now needs to fuse the granule descriptors in GPT-L1 table to higher sizes opportunistically. So we tried several approaches. The first approach that we tried was the brute force mechanism. So the figure tries to demonstrate the scheme that is done in EL3. So assume that we start in a fuse state, as in EL3 as part of boot up will try to fuse all the granules in the maximum possible block size. So we always start with 512 MB block size. And then when EL3 receives a delegate request from non-secure to the realm world for a particular page, this is the sequence of steps that happen. So EL3 would need to shatter that 512 MB block to 1632 MB block. And then it needs to pick the particular 32 MB block corresponding to that page and then further shatter it to 16 2 MB blocks. And then it picks up the particular 2 MB block corresponding to that page and then shatters it to 64 KB granule descriptor. And then it goes ahead and manipulates the GPI corresponding to that page and transitions it to the realm pass. So this is one situation. The other extreme situation is assuming that all the adjacent pages are already in the realm pass, and there is one last outstanding GPI which is still corresponding to the non-secure pass. And if we receive a delegate request corresponding to the last outstanding non-secure page, what EL3 now must do is it checks whether all the adjacent granule descriptors are corresponding to the realm pass. And if all the 32 64 KB granule descriptors are indeed realm pass, it then goes ahead to fuse it to a 2 MB block. And then it checks whether all the adjacent 2 MB blocks are in realm pass. And then it goes ahead to fuse all of that to a 32 MB block. Now it needs to check whether all the adjacent 32 MB blocks are in realm pass. If it is 32 MB, if it is indeed a realm pass, it goes ahead and fuses it to 512 MB block. So there is a lot of checking and operations happening at EL3 as part of this delegate and undelegate, which was not happening earlier. So this is one of the problems introduced as part of the brute force approach. Effectively, there's a lot of fuse and shattering potentially happening at EL3 as part of delegate or undelegate. So brute force without any tracking metadata, it is likely to be very inefficient for fuse. And there is also the issue that we need to hold the lock at the largest fuse block level, which can exacerbate the wait times. Now, the second prototype that we did is we tried to keep some metadata in EL3. The advantage of metadata is we avoid unsuccessful lookups. So if we look at this case too, the metadata keeps track of all the pages which are already in the realm pass, and when the last outstanding non-secure granule is transitioned to the realm world, EL3 will refer the metadata and then figure out that, okay, I have satisfied the condition to fuse all of the 32 blocks to a 2 MB block. And hence, it doesn't need to do a check of all the adjacent 32 entries to check if they are indeed realm pass or not. And also there is a case that all the previous delegations which happened prior to the last outstanding non-secure granule, all of them would have failed the check for fuse because the check would say that not all of them are in the realm pass and hence the fuse cannot be done. So there is a lot of unsuccessful checks that are happening. And it's only for the last outstanding one the checks actually succeed. And this scenario is now repeated in the higher level as well. only for the last outstanding 2 MB block, the checks actually succeed. And then we are able to fuse to a 32 MB block. So with metadata, we avoid a lot of unsuccessful lookups. And we can skip intermediate block creation if we find that a higher size is possible. For example, instead of transitioning the fuse from 64 KB to 2 MB, and then from 2 MB to 32 MB, and then finally to 512 MB, if the tracking metadata shows that all the entries corresponding to the 512 MB block are indeed realm paths, we can do the transition to a 512 MB block in one go without doing the intermediate steps. Now, having the metadata in EL3 has a memory cost, and as per our prototyping, it shows that we have about 1 KB of memory cost for every 1 GB of data that we need to track. And this is per world. So if we have to track for both secure and realm, it increases to 2 KB for 1 GB of data that we need to track. And this is too expensive to keep in SRAM. The CCA security model mandates that any EL3 critical data should be in SRAM, and this memory cost is not, we cannot have the scheme in EL3 because of the memory cost. So this is a deal breaker for this scheme. Now, the third prototype that we tried is move the tracking metadata to RMM. The way we do this is EL3 provides the fuse mechanism, but it doesn't make the decision to fuse. So the way this is done is EL3 will always initialize in the highest fuse state. And whenever it receives a request to delegate or undelegate, it will do the required shattering because all the delegate and undelegate requests are 4 KB sizes. And if we are beginning from a fuse state, we have to shatter to delegate or undelegate that particular page. But we will not fuse opportunistically. And EL3 then receives a fuse hint from the client, which is RMM in this case, and then proceeds to fuse according to the fuse hint. So the figure shows the scheme that is that I mentioned. So initially, EL3 starts with a 512 MB fused state block, and we receive a delegate request. So EL3 progresses to shatter it to the particular page, and then it transitions that page to a realm GPI. If it receives an undelegate request, it transitions the realm GPI, and we break the initial 512 block into a non-secure GPI corresponding to that. When RMM, since it's keeping track of all the delegate and undelegate requests, it detects that a 512 MB fuse can be performed. It sends a fuse hint to EL3. And once EL3 receives that fuse hint, it goes ahead and fuses the 512 MB block in one go. So it has the benefit of having the tracking metadata in EL3 in the sense that we don't do a lot of unsuccessful lookups in the attempt to fuse, because RMM, since it has the tracking metadata, it will only send a request when it knows that a fuse is indeed successful, is indeed possible. And also it has the advantage that the fuse policy can be determined by the client based on requirement. And hence the client can dictate the aggressiveness of the fuse. So it could be that we don't need to fuse all the pages that are delegated to the realm world, but only pages that have a corresponding mapping in the SMMU, which is not there present today, but in future, when we have device assignment for CCA, there would be SMMU mappings in RMM. And only for those mappings, RMM would request a fuse. So RMM can decide the fuse aggressiveness. EL3 doesn't need to unilaterally fuse. Such a scheme may be possible for the secure world. Yeah, and perhaps it is possible to have a hybrid approach that EL3 can provide brute force method if a particular world is not able to provide hint bit because it is not keeping track of all the delegations and undelegations. So that's the third prototype that we did. Now, before we discuss the future or the solution that we are going ahead with upstream, there is one another problem that we need to be aware of. Because all of the delegate and undelegate requests are happening at 4 KB granule, assume that we need to delegate a 512 MB block from the non-secure world into the realm world. So when we do have fusing or when we do have contiguous block in EL3, this is what would happen. Basically, when we receive the first, when we receive a 4 KB request, this is the life cycle of a particular 4 KB GPI, at least for most of them. There are exceptions for the first and the last granules, but for most of them, this is the life cycle. It would get shattered to a 32 MB block, then it would get shattered to a 2 MB, it would get shattered to a 64 KB. Finally, it would get changed to the GPI for this 4 KB granule would get changed, and then a corresponding fuse would happen. So effectively, a particular granule or most of the granules or the GPIs would have a transition from in all of these states, which is not efficient because if we have to transition a 512 MB block from non-secure to realm, if we were doing it in one go, we could have done it. We could have transitioned all of the 512 MB GPIs in one go and then issue TLBIs corresponding to that. But now we have a lot of intermediate transitions, and when we looked at the TLBI operations, it was probably around the region of 100K TLBIs that were being issued for a particular 512 MB block because all of the transitions that are happening. So this is certainly not efficient. Now, if we were able to do it in one go, then we could have done it as a single request, and we think that some of the issues with brute force also is avoided because since we are not shattering and fusing, all of those issues with unsuccessful lookups as part of fuse, all of those are not present. So today we have the situation that the RMM ABI for delegate are 4 KB based, and essentially if we wanted to do a block fuse, we need a change in the RMM ABI. Without that change in ABI, we think this will affect the realm launch and teardown times. So yeah, this is another problem that we need to keep in mind.
Soby, one question that might relate to RMM ABI change. Actually, in slide 7, when the last operation is to actually query fusing at the bottom of the picture, is it actually a new ABI or conflated into an existing ABI? This operation of fusing to 512 MB directed by the client.
Right. So this fuse hint operation is really, it's not visible to the non-secure world. This is an internal EL3 or an implementation defined EL3 RMM interface. And this is transparent to the non-secure world. The ABI that is actually visible to the non-secure client is this RMI delegate and RMI undelegate calls.
Okay.
So this fuse is actually something that, because RMM is keeping track of all the delegations and undelegations, it can detect when a fuse is likely to be successful, and then it sends this fuse hint to EL3, but this is not exposed to the non-secure client via the ABI.
Yeah, so this is kind of a new private interface between EL2 and EL3?
Yes, between RMM and EL3.
It's not an RMM ABI change.
It is not an RMM ABI change.
Okay, I see.
So,
thank you.
Yeah. Okay. So yeah, so in this slide, I would like to discuss what we are proposing for upstream. So we have this following dilemmas which we are not able to resolve today. So one of the problems with brute force is, as I mentioned, there's a lot of overhead in unsuccessful lookups that are happening. Now, if we were to restrict the fuse to the 2 MB block, which is the first level of fuse, potentially we can avoid a lot of the overheads which are occurring for higher sizes, say the 32 MB and 512 MB. Now, what is not clear to us is what is the benefit of fusing beyond 2 MB. We know that there is certainly a performance benefit in fusing to 2 MB, but it is not clear to us what is the benefit of fusing beyond 2 MB. So potentially, if we were to say that there is no benefit or there is no much benefit in fusing beyond 2 MB, then the argument can be made that EL3 can restrict the fuse to 2 MB, and hence the overheads involved, or perhaps the overheads involved in the brute force approach, is palatable, and we just stick with that approach, right? So the current dilemma is we don't know what is the benefit of fusing beyond 2 MB. The other dilemma is, we know that theoretically prototype 3 avoids a lot of problems with the brute force approach, which is prototype 1. But how much better is it? Can we measure that improvement? That is we don't have data for that today. Yeah, so that is one of the dilemmas. Now, the third issue that we have today is without the block mapping ABI, what is the measurable impact in realm launch times? Because as discussed in this slide, if indeed there is this shatter to all these intermediate block sizes and then have fused to the final block size, how does it impact realm launch times? What is the impact? We don't have that data today. If RMM ABI does introduce block mapping, then perhaps the issues mentioned for the brute force approach prototype 1 are insignificant, and hence we can stick with brute force approach. So all of this data we don't have at this moment in time. So what do we do for upstream? So I have outlined a plan for upstream approach. Essentially, we go ahead with the brute force prototype 1 approach, but limit the default block size to 2 megabytes. We will provide, TFA will provide a configurable option to increase the block size up to 512, but by default, we will keep it to 2 MB. Once we get feedback on some of the questions, as I posed in the earlier, then we can change the implementation in upstream. And we would need a solution that works for different workloads, both in the non-secure world and the realm world. So this is the current approach that we are taking for upstream. If there are no questions, I would like to move on to the fine-grained locking strategy for the GPT tables. Are there any questions till this point?
Hi, Soby. Is it possible to have realms that are based on different block size? So, for example, if we have
in automotive, we may have one big VM, one big realm, and then multiple small ones. In that case, we may want to have the 512 for the big, the big realm, but keep the 2 meg for the other one.
Right. So if the total size of the realm VM is not larger than 512 MB, then RMM would or RMM or EL3 would only try to fuse it to the next possible size, which is 32 MB or 2 megabyte. Yeah, there is no particular information with respect to the block sizes to be used, which are passed today from the non-secure world. The general input that we have received is if we can fuse it to the highest possible size at EL3, that is the best case scenario, because it gives the possibly it gives the best performance. We have less TLBI shattering, but we haven't seen a particular requirement to restrict the block size to a smaller size for a particular realm. We haven't seen that requirement yet.
So I think the context, is with Sophie, where you have one Linux realm and maybe 2 or 3 QNX realms. The sizes will be, I guess, very different.
Right. Now, since the permissions, although these are different realms, at the GPT level, all we are tracking is whether this address is restricted to realm pass or non-secure pass. It is not tied to a particular realm. So if indeed this Linux VM and this smaller VMs are adjacent in their memory layout, it might be possible at EL3 level to fuse it and have a 512 MB representation at the GPT level. Because at GPT level, it's just about permissions, whether this address is restricted to realm or this is restricted to another particular security state. Yeah, so depending on the layout of the addresses, the physical addresses of these particular VMs, EL3 would just go ahead and try to fuse it or represent it at the highest block size that it is configured to do so. It may not make much difference to the realm itself with respect to whether this GPT representation at EL3 is 512 MB. Yeah, that's what I think.
Thanks a lot.
Okay, so this is so Alexei's work. It also includes fine-grained locks for the GPT access. Today in TFA we have a big lock which is acquired by all the CPUs, and then all of the CPUs have to wait for this particular lock to make any manipulation to the granular protection table. So what Alexei's patch does is we try to introduce a finer level lock for GPT access. Now the locking scheme that we have taken up is what we think is the smallest granularity possible for this fine-grained lock. It needs to be at the highest fuse block level size. So if the highest fuse block level size that is going to be supported by TFA is 512 MB, then we think the smallest lock granularity has to be 512 MB. It may be possible to have lower or smaller granularity lock, but because there are complications if we go smaller than the highest block size, we may have to do a hand-over-hand locking scheme. And it's not clear to us what the performance improvement is from if we go lesser than the highest block fuse size. And the memory cost is also another important factor. So today, what we have done in TFA is we've implemented a bit lock, a bit per 512 MB, which translates to about 256 bytes of SRAM for one terabyte of PA space. Yeah, so this seems to be the lowest footprint lock that we can implement. One thing which we need to be aware of is today we have only CPU-only realms, and hence the GPT tracking at EL3, we only do the DDR, we only do the L1 tracking for the DDR that is present in the system. But when we have device assignment, we have to cater for the device addresses as well. And the granular protection table needs to cover the device IO as well. So potentially, it could be that we may have to cover a huge PA space at EL3. We have to implement this lock for a huge PA space, potentially up to maybe 48-bit of PA space. So the current bit lock scheme that we have, it has the following behavior. The lowest granularity that the mutual exclusive that the architecture provides is a byte. So we've implemented a bit lock over the byte lock exclusive accessors that are present in the architecture. So when locking, we acquire the byte to set a bit in that particular lock byte. And when unlocking, we acquire the same byte and then we clear the bit. So this has more overhead than a typical spin lock, but it has the advantage that we have a bit per lock, and then we can compress the memory footprint required for the lock. So this implementation is now present as part of the patch stack in review. We've introduced new bit spin lock accessors for this purpose. Yeah, so this is the final slide. So the upstream patch is available here for review. And based on feedback related to performance or any of the questions that I have posed in the previous slide, in future we can change and we can pivot accordingly in EL3 firmware. Yeah, if you have any questions, please feel free to ask. Okay. There are no further questions. Over to you, Olivia.
Thank you. The only practical question I have is in terms of the single patch. Actually, it aggregates a number of different changes or concepts. I wonder if it would be worth splitting into smaller patches.
Yes, I think, yeah, that's one of the review feedback for the patch. Yeah.
Okay.
Yeah.
I have not yet reviewed thoroughly, but that's my first observation.
Mm-hmm.
Yeah.
Yeah, because some of this work was prototyped internally.
Yeah.
I think, yeah, this was done as a single patch in the upstream. But I think, yeah, we can split it further. Yeah.
Thank you. Any other question or business? Okay, if not, I will stop the recording. Thank you, Soby and Alexei.
Okay.